Reading quiz for 1-4, where you learned how to multiply a matrix times a vector, one of the things that you learned. So it said the definition that the book gives for a matrix times a vector is it says take each column of the matrix and use the corresponding entry from the vector as a weight. Okay, so this would be, I use 3 as my weight and times the first column, 0, 1, 2. And then you put the 4 as your weight on the second column, 6, 7, 8. And then you use the rules of vector multiplication and addition. So 3 times 0 is 0. So I'll just do this. 0, 3, 6. Multiplying a vector times a scalar, you multiply every entry by the scalar. And then my other vector is going to be 24, 28, 32. And then to add vectors, you add component-wise. So this is 24, 31, 38. All right, what is this matrix called? 1's on the diagonal, 0's everywhere else. Oh, we're going to call it the identity. It is a if you wrote reduced echelon form, I'll take that. It is in reduced echelon form. But I was looking for the identity. The identity matrix, or we shorthand it I with a subscript for the size of the matrix. That's I3. It's the identity 3 by 3 matrix. What makes it the identity? What does that mean? Yeah. Yeah. So if we're talking just the real numbers, just one real number line, what's the identity element in the real numbers? 1. Yeah. And it's the identity because when you multiply 1 times anything, you get that thing. So in matrix land, the identity is 1's on the diagonal, 0's everywhere else. Because when you multiply the identity matrix by a vector, let's just do a 3 by 3. You're going to get the vector. Yeah. If I multiply this by any vector A, B, C, remember the rule we just learned, you take each column, use the entry of the vector as a weight. So this is A times 1, 0, 0, plus B times 0, 1, 0, plus C times 0, 0, 1. And when you simplify this, you're going to get A, B, C. You get the vector back. So that's why that matrix is called the identity matrix. It's the thing that when you multiply by it, you get the same vector back. It works equivalent to the way 1 works in the real numbers. All right, true or false? If the matrix A has a pivot in every row, then the equation AX equals B will be consistent for every possible choice of B. Yes, that is true. Yeah. So basically, if there's a pivot in every row, that means that you'll never get 0 equals a number, which is the sign of inconsistent, right? Because you've got a pivot, so there'll be a number there. So this is true. So we're going to learn even more notation to represent a system of linear equations. We talked about a bunch of it in the quiz. And we're going to be able to tell if a set of m by 1 vectors, or alternatively, the set of columns of an m by n matrix spans Rm. So that's, we'll get the word span again, using it in a slightly different context. Okay, so I've got a system of linear equations. 2 equations, 3 unknowns. I can write this 3 different ways. I can express this system 3 different ways now. Vector equation, matrix equation, augmented matrix, plus just writing out the system of equations. So we've got 4 ways of expressing the same thing. All right, so my vector equation is going to be the weights or the unknowns. Okay, so I'm going to have an x1, and then the vector is going to be the coefficients, 3 and 1. Right, so x1 times 3, 1, that says 3x1 is my first entry, so my first equation, and just an x1 is the first entry of the second equation. Plus, then I'm going to have an x2, my unknown weight, and then the coefficients here are going to be 2 and -1. And then my next unknown weight is x3. Its coefficients are 7 and 1. And does that equal 5, 8? So now if you read all just the top entries, right, this says 3x1 plus 2x2 plus 7x3 equals 5, which is the first equation. And then if you read the second entries, this says x1 minus x2 plus x3 equals 8, which is the second equation. I know I'm moving it on purpose. Okay, so if I want to write it as a matrix equation, remember the definition of a matrix equation was you take the vector, it's going to be a matrix times a vector. The things in the vector are your weights, and you put those on the columns. So I'm going to have a matrix times a vector, and my vector is going to be my weights, x1, x2, x3. So x1 is the weight on your first column, so that would have to be 3, 1. x2 is the weight on the second column, 2, -1. x3 is the weight on the third column, so that's a 7 and a 1. And does that equal 5, 8? So you'll start to notice the patterns here, right? So the matrix is called the coefficient matrix, right? It's got all the coefficients in it, but not the 5, 8, right? Not the stuff after the equal sign. It's just a coefficient matrix. And then your augmented matrix, it's the coefficient matrix augmented with the stuff on the other side of the equal sign. So I'm going to have 3, 1, 2, -1, 7, 1, augmented with 5, 8. So we have 4 ways of expressing the same question to solve that system of linear equations. And just like with any time that you have different methods of expressing the same thing, the reason there are multiple methods is because some of them lend themselves better to certain kinds of problems. So right now we're just developing some fluency between the 4. But to solve this system, for all of these, the method we would use to solve it is to RREF the augmented matrix. We do the algorithm that we learned past couple classes. Okay, so remember from the reading and from the quiz, the product of a matrix A and a vector X produces another vector, AX. And the way you do it is it's a linear combination of the columns of A using the corresponding entries in the vector X as weights. So we're going to practice multiplying a matrix by a vector. And there's actually another way to think of the multiplication. I'm going to show you the 2 ways. Because again, sometimes one is easier than the other to think about. All right, so I'm just going to draw a line here so that we can have room for our 2 methods. So for this, you take each column, use the corresponding entry as a weight, and then add them together. So I'm going to have 1, -3, 1 with a weight of -2. Sorry, my phone. And then 2, 1, 6 with a weight of 3. Turn this off. So I'm going to have -2 plus 6 is 4. And then I'm going to have 6 plus 3 is 9. And negative 2 plus 18 is 16. Oh, perfect squares, like that. Okay, another way to visualize, another way to do this computation, it's just a slightly different algorithm. And there's sort of a visualization thing that I do that goes with it. So you take each row and you take its dot product with the vector. So here's my first row, and there's my vector. So before I even start, I want to know what the result is going to look like. Pretend I didn't do anything yet. So this matrix, what are its dimensions? 3 by 2. 3 rows, 2 columns. This is 3 by 2. And then the vector, that's a 2 by 1. So the reason I know that I can multiply those two together is because the inner dimensions match. We get the 2's match up. The result is going to be the outer dimensions, 3 by 1. So my answer is going to be a 3 by 1 vector with 3 entries. So I'm going to build my vector. I'm going to make it nice and big because I'm going to do computations within it. But the answer is going to be a vector with 3 entries. So I'm just putting 3 blanks there for myself. All right, so each one of those entries you calculate by taking the dot product of each row with the vector. Do you guys know dot product? Yeah? Okay, well, I'll tell you what it is anyway. So you take the row and you dot product it with the negative 2, 3. That means, visually, this is what you do. Take that 1, 2 as a horizontal item, right? Imagine picking it up off the board or off your paper, rotate it 90 degrees, and lay it on top of the negative 2, 3. Okay? The things that match up, you multiply together, and then you add the results. Okay? So I'm going to have my 1's going to be on top of my negative 2, so I have 1 times negative 2, plus then add the 2 times the 3. Then you do that 2 more times. For each row, you dot product it with the vector. So my negative 3, 1, now I'm going to dot product that with negative 2, 3. So again, imagine you take your negative 3, 1, rotate it 90 degrees, put it on top of the negative 2, 3. The things that line up, you multiply, and then you add the results. So I'm going to have negative 3 times negative 2 plus 1 times 3. And then finally do it for the last row. 1 times negative 2 plus 6 times 3. And then simplify. So this says negative 2 plus 6 is 4. This says 6 plus 3 is 9. And negative 2 plus 18 is 16. So you're doing the same calculations in both cases. It's just like slightly different ways of writing it down. So in general, you can use whichever one of these feels more comfortable to you.
Certain circumstances are will in second method.
Yeah. Yeah, once we start multiplying, instead of just a matrix times a vector, if we did a matrix times another matrix, I often like this method better to keep track of all your work. All right, so similar thing in the next one, it's just that I'm multiplying my vector as a vector of unknowns rather than constants. So we'll do 2 different methods. First one, use each of these unknowns as a weight on the corresponding columns. So I have x1 times 1, 1, negative 3. You'll notice that I sort of vary where I put the constant. You can put it before the vector or after the vector. It's just multiplication, so you can go either way. Put it wherever you like it. Plus x2 times 3, 5, negative 7, plus x3 times negative 4 to 6. Of course, I didn't estimate the room I would need. So that's it. There's nothing else we could do. Well, actually, that's not true. I guess I could multiply by the constants and simplify. So this would say x1 plus 3x2 minus 4x3 is my first entry. And then multiplying your scalars times each of your second entries would give you x1 plus 5x2 plus 2x3. And then multiply your scalars by all of your third entries, and you have negative 3x1 minus 7x2 plus 6x3. And you can see this is where you would end up if you had done the original, if you had done the other method, right? If you take this first row and take its dot product with the first column, imagine pick that up, turn it 90 degrees, lay it on top, you had 1 times x1 plus 3 times x2 minus 4 times x3, which is exactly what we have in this first entry. So it's just another way of finding it. Okay, here are many questions that all mean the same thing. We looked at the first 3 of these last class. Is 4, 12, 4 a linear combination of 2 given vectors, right? I'm asking, are there weights? This is asking, are there weights, some unknown, you could call it x1 or x2 or a and b. Are there weights that you can put on these 2 vectors so that when you add them together, you get 4, 12, 4? That's the exact same question as, is that vector contained in the span of those 2 given vectors? Because the definition of span was the set of all linear combinations. So if 4, 12, 4 is a linear combination, it is in the set of all linear combinations. And then again, is 4, 12, 4 contained in the same plane as those 2 vectors? That's just a geometric way of asking the same question. Now I've got some more versions of that same question. Is there a solution to this system of linear equations? Is there a solution to this vector equation? Is there a solution to this matrix equation? Is the vector contained in the span of the columns of the matrix? Okay, so instead of saying, is it in the span of those 2 vectors, you could use those 2 vectors to make the columns of a matrix and say, is it in the span of the columns? A couple more. Is it a linear combination of the columns? And the way you would answer all of these is row reduce the augmented matrix that's associated with all of those equations. All right, so here's sort of a little summary of the section. If A is an m by n matrix, all of these statements are either all true or all false. So if I ask you about does it span the columns of A, right? If you can answer any of these as yes, you've answered all of them as yes, right? So you pick the question that's easiest to answer, and then you know the answers to all of them. So it says that R sub m, remember that's the set of all column vectors that have m entries. So if the matrix equation AX equals B has a solution no matter what column vector in Rm you put in for B. Okay, so this is never inconsistent, no matter what you put on the other side of the equal sign. That is equivalent to every column vector B can be expressed as a linear combination of the columns of A, which is equivalent to the columns of A span Rm. Okay? That means that the span of the columns of A, so you put scalar weights on the columns of A, add them together, that you can build all of Rm. You can build all of M space by taking linear combinations of the columns of A. And quickest way to answer any of those questions is to look at your pivots. There's a pivot in every row, then all of those questions are yes. Because if there's a pivot in every row, you'll never get 0 equals a number, right? So that pivot prevents that from happening. Okay. So here's a matrix A. If I ask the question, do the columns of A span R what, right? The only sensible number to put in that box, say, okay, if I'm looking at the columns of A, so think of those as separate entities. Each column of A, 1, 2, 0, 1, 2, 0, 1, 3, negative 1, and 0, 0, 1. Each column is a separate thing. If I'm going to look at the span of those things, that means the set of all linear combinations, right? So you're going to put scalar weights on each column, add them together. Where does the result live if you take a linear combination of those 4 columns? No, it's not augmented. R3 or R4? R3, yeah. So if I write it out, I'm just going to take a linear combination of the columns of A. So I've got some unknown weight, put an unknown weight on each of my columns. If I had values for A, B, C, and D, and I just multiplied and added, the result would have how many entries? 3, right? So my result would have 3 entries. One, I'm not going to put circles because they look like zeros. Right? I'll put stars, star, star. There would be 3 entries in the result, which means that the result lives in R3. So I can only ask, do the columns of A span R3? Yes.
Wouldn't the easier way to look at it just
Yeah. Yeah, you could also say how many pivots. Yeah. So if I want to express the question in 6a using the first bullet from number 5. So let's go back and say this bullet, it says the matrix equation AX equals B has a solution no matter what B you choose. So I'm going to say A 1, 2, 0, 1, 2, 0, 1, 3, negative 1, 0, 0, 1 times my vector of unknown weights, which, how many weights do I have to put in there? Unknown weights. 4, just like I did up here, right? I have to have an element in here as a weight for each column. So I'll call them A, B, C, and D. You might call them X1, X2, X3, X4. Doesn't matter. Okay. Equals. Now, when I do this multiplication, when I put my weight on each vector and add them together, my result has 3 entries. So we're going to call this B1, B2, B3. So this has a solution for every B1, B2, B3 in R3. That V thing means for every or for all. If I want to express this same question using the second bullet from number 5, sorry, people are still writing. I'll pause. All right, so the second bullet from number 5 said, every column vector can be expressed as a linear combination of the columns of A. So this says every vector B1, B2, B3 in R3 is a linear combination of the columns of A, which is 1, 2, 0, 1, 2, 0. These are questions. Right?
is that all of
a linear combination of, I use that that shorthand a lot for linear combination. All right, so if I want to answer this question, right, is there always a solution? Can you always find weights, A, B, C, and D, to build any vector in R3 you want? So we've done this where I give you a vector B1, B2, B3 and say, can you find weights, right? But is it possible to say that you can do this no matter what B1, B2, B3 I give you? So we've done this for specific ones. We want to see what happens if I do it for a general. So basically, I'm going to write out my A here, my augmented matrix, 1, 2, 0, 1, 2, 0, 1, 3, negative 1, 0, 0, 1. If I augment that with any vector there, so what we've done prior to right now is I've given you a vector like 5, 1, 12 or something, right? And then you can tell if this is consistent. I want to know, is this going to be consistent no matter what I put here? So I'll put like a B1, B2, B3. No matter what I put there, can I find weights that will build B1, B2, B3? So what I do is ignore this for now, right? I can just look at the coefficient matrix, and if there's a pivot in every row, as long as I don't have a row full of zeros, this won't be inconsistent, right? There's no way I'll get 0 equals a number, and that's the sign that there's no solution. So I want to just look at the pivots. So I'm just going to RREF the coefficient matrix. So I've got 1, 2, 0, 1, 2, 0, 1, 3, negative 1, 0, 0, 1. RREF it. That squiggle means is row equivalent to. And I get 1, 0, 0, 1, 0, 0, 1, 1, 0, and 0, 0, 1. So I have pivot, pivot, pivot. So regardless of what's augmented over here, regardless of what happened to these numbers when I did all my work, this will be consistent. So pivot in every row implies consistent, which means the answers to all my questions is yes. The columns of A do span R3. No matter what vector I put here from R3, there will be a solution. So once you know that, this question is super easy. Is 1, 2, 7 a linear combination of the columns of A? Yes. Every possible vector in R3 will be a linear combination of the columns of A. We just showed that no matter what B1, B2, B3 I pick, the answer to that is yes. Let's not find the weights. I don't feel like it. Okay. If I did want to find the weights, what would I do? Yeah, you'd put A here, and then you'd augment with 1, 2, 7, and find the solution. So you'd find the weights.
You want to use like that one
yeah, it wouldn't be helpful because you can't just put 1, 2, 7 here, because then it would say that the weights are 1, 2. Well, no, something 2, 7, right?
You could left the B's in there.
If you had left the B's in there and modified as you did the row reducing, yeah. Which is actually what I did the first time, which I thought this question would have been easy to answer, but then I decided not to write it down, and oh well. All right, so that's it for the lecture portion for 1.4. You can jump into the activities. You've got 35 minutes to try to get through those.